It's the time now to talk about analog to digital converter. Analog to digital converter is a circuit which will convert the sample signal to digital. But keep in your mind, there are many circuits used for that purpose, many techniques used for that purpose. Here we are going to study only the flash type, or we call it flash analog to digital converter, where the flash analog to digital converter depends on comparator. To do the process of conversion, we depend on comparator, and this is considered as one of its disadvantage because it needs a lot of comparator to do the process of conversion. The number of comparator required for this analog to digital converter can be calculated as you see here. Number of comparator is equal to 2 to the power n minus 1, like where n is the number of bits. So if we have 3 bits, we have a 3 bits analog to digital converter. That means we are in need for 7 comparators. We are in need for 7 comparator to perform the analog to digital conversion. Here is example. If 10 bit, it's the same thing. It's going to be 2 to the power 10 minus 1, which equal to this value. Now, in a simple way here, I'm not going to go to the detail here, but in simple way, the comparator will compare the signal coming from this point, which coming from the sampling signal, with the signal coming from here, which coming from the reference. And the result will come on the output. So the output signal, if you think of it, you are going to find that the output signal going to be sometimes 1, 1, 1, 1, 1, 1, 1. When I say compare means we are going to assume if they are equal, the output 1. Otherwise, it's 0. Maybe something like this. Other times, you are going to find that it's going to be something like 1, 1, 1, 1, 1, 1, 0. Other times you will find, other times means other comparison, other value entering. Others going to be 1, 1, 1, 1, then 0, then 0. So notice that the values on the output going to look like start from 1, 1, 1, 2, 3, 4, 5, 6, 7, 8. And here 0, 1, 1, 1, 1, 1, 1, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, and so on. So each of these values going to meet digital value. Digital value means digital value out of it 3 digits. So we can make it such that it's starting from 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, and so on. So each of these values going to be stored here or kept here. Whenever this value come, for example, we will find on the output 1, 1, 1. Whenever this value come, we will find in the output, maybe we can make it such that it's 0, 1, 1. Whenever this value come, we can find in the output something like 1, 0, 1, and so on. So this is the digital quantity equivalent to this analog signal. Some concepts and terminologies here, I think they are clear now. We are clear about these elements. It's nothing new with it. Maybe most of them are not new. Like the offset, it's the minimum analog value. Offset, minimum analog value. That means if there is a value below 0, it's the value which coming below 0. It needs to be jumped to 0 because in analog to digital converter, negative cannot be detected. That's why whenever we have any value below 0, if this is 0, below 0, we will add offset to it to move it to the positive. Span is the maximum minus the minimum. Maximum voltage minus the minimum voltage. So if the signal is 5 volt to 0 or 0 to 5 volt, that means the span is 5. A step size, that's what we discussed earlier. It's the quantum interval, which going equal to the span over 2 to the power n. That's discussed earlier already. This resolution is the number of sample to be taken. Now, if I want to convert the conversion analog number is equal to the digital number multiplied into the step size plus the offset. That means I need to convert from digital to analog. So I will put the digital here. Of course, we are putting the digital in decimal form. we are not putting it in binary, we are putting it in decimal form. Now, how about if I want to convert from analog to digital? If I want the digital and I have the analog, we are writing it such that the analog minus the offset divided by step size. Okay, let us consider this example, which we hope to make us clearer about the process of conversion. Here we have digital to analog converter, 6-bit digital to analog converter. If it's 6-bit means digital to analog means the input is digital in this case, 1, 2, 3, 4, 5, 6, where the output is analog. The input have this value at entering. What will be the output? That's the idea. But he mentioned something else. He said the range of the signal expected on the output will be from minus 2.5 to 5. When we did the planning at the beginning, we assumed that the range of the ADC is going to be minus 2.5 to 5. Okay, so if this signal entering here, what will be the output? So first of all, we need offset because we have minus quantity, minus value. As I said, minus cannot be understood by the device, so I need to make offset here. So the offset is equal to minus 2.5. The span or the range is equal to 5 minus 2.5, which is equal to 7.5. Then the step size, I hope you are clear about step size. For each step, equivalent to what? It's equal to 7.5 over 2 to the power 6, which equal to 0.1172 volts. So each step equal to this value. Now I can calculate, now the analog signal will be equal to the digital value. Digital value means this value, but again I have to express it in decimal. I have to express it in decimal for this formula. So in the question, he gave the value to us in the question. So he said this is the digital, which equivalent, or this is the digital value, which equivalent to this decimal. So it's going to be substituted here. Step size, digital number multiplied into the step size minus the offset equal to minus 0.039 volts. So the output here, when this input comes here, this output will be shown at the output of the analog to digital converter. Another simple example, he's saying here, given analog signal with a range of minus 5 to 5 and 8-bit ADC. Determine the offset. Offset will be minus 5. Offset is the negative quantity, which is the value below 0. Then the span. Span will be 5 minus 5, which equal to 10. The step size, 10, 10, which this value, the span, will be here, divided by 2 to the power 8, where 8 is the number of bit. So it's going to give us 39.1 millivolt. Here we have an example on analog to digital converter. Example means whatever available in the market. This kind of converter available in the market. It's a chip having this shape. Chip means IC, which having a number of ADC 0804. So its input is analog, as you see here. The analog is going to pin number 6 and 7, and the output will be starting here from pin number 11 to pin number 18. The other pins are described in the next slide, so you can see the other pins in the next slide. But I want you to know that for analog to digital converter, which IC chip, the most important thing is to identify the input signal, the output signal, and VCC, which is the power supply to the signal. The power supply to the signal. Okay, means we need to supply the signal, the chip, with VCC, and after that we can send input to get output. Of course, the other pins needed sometimes. You need to send a certain kind of signal to certain kind of pins to get the process operate, or the operation performed. You will see this in the next slide. So here are the pins with their description. I'm not going to read them in detail. I just want to read, for example, this one, number 4. It's a clock N. Clock N means it's external clock, can be connected here, else RC can be used for accessing internal clock. So we can have clock circuit to generate a clock and connect it to this pin, or we can connect RC to generate that kind of signal. VCC, the one I mentioned, it's between a 20, it's a VCC. So we need to supply the power supply at VCC. The ground, number 10, we need to connect between VCC and the ground. So anyway, the pins are there. If you are interested, you can go to the detail of the pins to know how to connect this kind of circuit physically. ADC 0804 have some properties as I discussed earlier. So it's having 20 pin. It's converting differential input to 8-bit output. It's having internal clock, and it's having a ground for the digital signal and the ground for the analog signal. So these are the kind of features for ADC 0804. Conversion is part of data acquisition system. So here we will start talking about the conversion, where we will start with current to voltage conversion, the current to voltage converter. So if the instrument is producing current on its output, you know, instrument is going to measure certain quantity. If the quantity is converted to current, that means we need current to voltage converter to convert it to voltage, so that I can easily process it, or we can easily send it to the computer and so on. Now, how to convert the current to voltage? We can simply use something like resistor with battery. This is a resistor and this is the sensor. We can do this, but actually I'm not discussing it because it's not advisable, since if you want to use this method, the resistor of this device is supposed to be very, very high. So it's not guaranteed for us that it's going to be high. That's why we don't advise this method. It's very well known. Everybody knows if current goes to resistor, the output will be voltage. So we can say we can use this method, but this method is having a problem of the resistance value. That's why it's preferable to use the method in the next slide, which here this method. In this method, we are going to use the operation amplifier. So whenever you are asked to convert current to voltage, use this circuit. Don't use any other circuit, because this is applicable everywhere. The circuit is nothing but amplifier with feedback resistance, as you see, and the current is going to be connected to the input without resistance at the input. Okay, so now the output voltage here is equal to IP into RF. IP, the current here, into RF. That means whatever the current IP is going to be converted to a voltage. That's how we can convert the current to voltage. Something very simple, where the Vout is the output voltage, IP is the current which to be converted, it's the input current, and RF is the feedback resistance of the amplifier. Resistance to voltage converter. These circuits are very clear to us, very simple. Resistance to voltage converter, if the output of the sensor is resistance, like you see here, we can, this value RS, we can use this circuit to do the conversion. So how this can be? It can be by putting what we call voltage divider, as you see here, and the output is to be taken from the sensor by itself, RS. So now, if the voltage E applied, what will be the voltage on RS? The voltage on RS, which VA, can be calculated this way. So notice that the output voltage is proportional to the value of RS. Keep this in your mind. Any change in RS will make change in VA. So that's how I'm converting the resistance to voltage. Also, it's the same technique, but the voltage generated may not be high enough. That's why we need to put amplifier. I'm not showing the amplifier here. I'm not showing the amplifier. This is just a sample of amplifier. Whether it's inverting, non-inverting, any kind of amplifier is not shown. Or maybe instrumentation amplifier, I didn't show. Here, I'm just showing that there is amplifier. So this is to be used if the generated signal here is small. If it's small, we are going to send it to amplifier to amplify it. So the output will be similar to the previous one except multiplied into AV, multiplied into the gain of the amplifier. Let's see this example. In this example, he said consider the circuit shown RS equal to 370 ohm, RS 370 ohm here, 370. R node equal to 620 ohm. The battery is 6 volt here, 6 volt, and the amplifier gain is 5. This amplifier is 5. Calculate the output voltage V out. So we need to know what is this output voltage. So you can put the equation one shot, all the equation you can put it one shot as I mentioned, or you can calculate the voltage then multiply it into the gain. So this part is to calculate the voltage on RS and then multiply it into the gain. So this is to calculate RS multiplied into the gain. You will get the value equal to 11.2 volts. So the voltage here is 11.2 volt. We need to consider that there is a ground here and this is ground here. So this point and this point are the same in this circuit. Resistance to voltage conversion again can be used by this Weston bridge, if you remember Weston bridge. So in Weston bridge, we have resistor R node, R node, R node, and here RS. So keep in your mind that in balance, when VA equal to VB, the output will be 0. When VA equal to VB, that means the output will be equal to 0, because whatever the gain here, the voltage between point A and point A0 multiplied into the gain will give me in the output 0. If VA not equal to VB, then we are going to find the output is equal to VA minus VB multiplied into the gain. If VA not equal to VB, that means there is voltage VAB. Multiply it into the gain, you will get to the output voltage. The derivation of VAB shown in the previous slide is similar to what we have discussed in Weston bridge. So this is VA, this is VB. VAB is equal to VA minus VB. So when you subtract them, they are going to end up with this equation. So here is VAB. That's how we can calculate VAB. Okay, now V out is equal to gain into VAB. So whenever you get circuit similar to the previous slide circuit, you will calculate VAB from this equation, then multiplied into the gain to get the output voltage. We will consider this example on the resistance to voltage conversion, where in this example, you will read it. Let me discuss it here. We are having the Weston bridge with 300 ohm resistance here, 300 ohm resistance here, 300 ohm resistance here, and this is sensor. The sensor have a resistance of 300 ohm as well. Now the sensor is heat sensor. Before we apply heat, it was 300. After we apply heat, the resistance here become 400 ohm. He gave another another elements given. He said the gain of the amplifier is 35 and the voltage of the battery equal to 12 volt. Calculate the change on the output voltage. Look, he doesn't want the output voltage. He wants the change in the output voltage when the temperature increase or when the resistance increase from 300 to 400. Let us see in the next slide. So in the answer of this question, RS is equal to 300, VAB equal to 0. That's because the bridge is balanced. Why the bridge is balanced? Because all the resistors are equal. So VAB equal to 0. From there, we can calculate the output voltage as V out equal to the gain into VAB, which 230 into 0 equal to 0 volt. Now, when RS become 400 ohm, VAB can be calculated from this formula we will calculate it to find that VAB equal to 0.213 volt. Now the output voltage equal to the gain into VAB, which equal to 7.45 volt. Now if you want to get, actually this is the change in the voltage. Why? Because the change of the voltage is V, let's say 1, or V before the first V equal to 0, second V equal to 7.45. What I mean by first and second, I mean the voltage on the output before the resistance change was 0. The voltage on the output after the resistance change is 7.45. That means that the change in the voltage due to the change in resistance is equal to 7.45. That's it for the analog to digital conversion and the conversion of the signal. I hope everything is clear. I wish you all the best. Thank you.